All right, students, today we're going to do our inquiry into simple electric circuits. And basically, electric circuits have resistance, potential difference, which is voltage, and current. So, voltage is equal to current times resistance. This is called Ohm's law. Okay? And Ohm was the person who discovered this, that voltage is equal to current times resistance. And so in this lab, we're going to just kind of see circuits and how they work and how voltage, current, and resistance relate to each other. Your house is wired in different circuits. And we're going to find out, is that a series circuit or is that a parallel circuit? We're going to also find out how resistance affects current. Because in our homes, we have a certain amount of voltage. We have 110 volts typically. But if you have like an electric dryer, it might be a 220 volt. Or if you have an electric stove, it might be on a separate 220 volt circuit. Or like a hot tub, you can have a 220. So, but typically in our homes, we're dealing with 110 volts, but that's another story. We're going to see how does current and resistance and voltage work together. We're going to be using a multimeter. With this, we're going to measure resistance, and we're going to be using a power source, which is going to deliver some voltage to our little experiments. Think of the voltage, think of the power source as kind of like a water pump. I like to think about electricity like I think about water flowing through a pipe, although you never want to mix electricity and water, but it kind of, you have the same kind of idea. There's electrons in your house, in the wires, and those electrons, as they move along, and that delivers electricity. Electricity is one of my favorite things because if we didn't have electricity in our homes, we would have to have a little motor on every single thing in our house. Imagine like how your lawnmower has a motor and you have to put gas in and oil and you got to prime it when you use it. Imagine having to do that for everything in your house. It would really be a full-time job just keeping everything with amount of gas and so on. But instead, we have this outlet in our house, and we just plug something in, and it makes things run, and it is just awesome. So I'm a little bit partial to electricity. All right, so in today's lab, we're going to be talking about current, resistance, and voltage and their relationship. We're also going to be talking about series circuits and parallel circuits. So let's look at, so we're just going to go through the lab page by page. So that was our first page. And now we're going to look at page 2, making predictions. Remember that voltage is equal to current. Oh, and by the way, current is measured in amps, and resistance is measured in ohms, and ohms look like a little horseshoe. And then we have voltage, which is potential difference. That just means that that electrons are flowing, they're moving. And again, if you think of the water analogy, think of this power source like a pump that's pushing the electrons through pipes. And we'll show how that affects things a little more. All right, so the first couple questions, making predictions, you're just going to be using like a mathematical equation, a mathematical understanding. If you increase V in a circuit, what is going to happen to R? What is going to happen to I mean the current. So if you increase V, and if R stays the same, I is going to do what? So these are just making predictions based on the formula. The second one says, what would happen if you increase the amount of resistance? So now you're increasing R, and V is the same, so what is going to happen to I? So it's kind of just getting you to work with that little formula a little bit and see how current and resistance kind of are related. And we'll get into that a little bit more in the lab. Now, our power source is set at a voltage output of 4.5 volts. 4.5 volts. So at the top of this page, the voltage is set 4.5 volts. That's what we're going to use. And what we're going to do is we're going to work on our very first data table. And to do that, we are simply going to follow these little diagrams. This squiggly line indicates resistance. Think of it as like your toaster. If you look in your toaster and you see those little pieces of wire, toasters, the wire in a toaster is highly resistant to electrons. That's why it glows. Okay? That's why you get your toast brown from that glowing, that little glow. If it was copper in there, the electrons would just flow right through. It wouldn't provide much resistance. But since, think of it like in our water analogy, think of it like there's a pipe with just full of rocks, and those rocks are providing the resistance. I like the water analogy. Anyways, that symbol is resistance. The M symbol is for our multimeter. Okay? And this V symbol, that is our power source. So this diagram just has the multimeter and the resistance. And this diagram has our power source, multimeter, and resistor. And both of them show a circuit which starts, goes through, and comes back to the pump. Think of it like water being pushed through pipes, and then it comes back and gets that push. Voltage is like a push. Okay? All right. So we've got 4 resistors here. And we are going to use these resistors to look, first of all, at our table here. Okay. Now, resistors, and these are old resistors, they're color-coded. And they have gold stripes or silver stripes depending on how accurate the amount of resistance is. It's within 5% accuracy or 10% accuracy, depending on what color stripe. So when you're trying to figure out the resistance using colors, okay, you go and find the gold or silver stripe. This one has gold. And then you read the color on the opposite end. So this one, for example, has a brown line, a green line, and another brown line. So it's brown, green, brown. Looking at the color code, we have brown, which is 1. We have green, which is 5. And we have brown again. The way that we write that, resistance from color, 1, 5 times 10 to the 1. The third color is the exponent. So 15 times 10 to the 1 is 150. Let's measure that resistor. And let's see what our multimeter says about it. Should be within a percentage of 150. So it should be close to 150. So I'm going to put my little clips onto the posts, and the reading is 150.5, 150.5.6.6, okay? So we said by the color that it was 150, and now our measurement is 150.6. Okay. Next, we are going to do our second resistor. And this one is brown, black, red. Okay? So we find the gold, and then we go to the opposite, brown, black, red. Okay? And brown, black, red. Brown is 1. Black is 0. Red is 2. So we have 1, 0 times 10 to the second. 10 times 10 to the second is 1,000. So when we measure the resistance, we should come up with a measurement close to 1,000. Wow. Exactly 1,000. That is definitely within the percent accuracy. So when we measured it, it came out to 1,000. Okay. Now let's look at our third one, which is, we look at the gold, we go opposite, it's brown, gray, red. Brown, gray, red. Brown, gray is 8, 1, 8, red is 2, so 1, 8 times 10 to the 2, which equals 1,800, and again, it's in ohms. That's our unit, ohms. I should write ohms. The chart says ohms on it. Remember, that looks like a little horseshoe. Whoops. That's from the colors. I didn't measure it yet. I wrote down 1,800 in there. Let's see what it actually comes out to. 18 is the actual measured, which is close to 1,800, so we're good. And our very last one is red, red, red. That's 2, 2 times 10 to the 2. So what should that be close to? 2,200. So this one is 2, 2 times 10 to the 2. 2,200, and we came up with 2,185. Very close. Okay. So now we're going to predict in this which one would have the highest current and which one would have the lowest current flowing through it. Now, let's think about this for 1 minute. If voltage equals I times R, current times resistance, V is going to stay the same. We're going to use that same power source, 4.5 volts. V is not going to change. So we have 4 different resistances. We have 150 all the way to 2185. We have a very low resistance and we have a very high resistance. If V is the same, which one is going to have the highest current? Which one's going to have the highest current? Very interesting. Would the one with the low resistance have a high current? Or would the one with the high resistance have a high current? Which one? So I want you to predict which one you think is going to have, just number them from 1 to 4. 1 meaning this will be the highest. Okay, so 1 equals the highest current, and 4 equals the lowest current. Okay, I want you to predict. This you will do on your own. Now we're going to actually measure the current with the multimeter and the power source. What we do is we look at our diagram. V is the power source. We're going to start with the power source. And by convention, we always go from red to black. So what is the red lead connected to if we follow this? The red goes to M. Okay? Red, and we're going to go to red, red to red. See, if we don't do it this way, we're going to short things out and we're going to blow a fuse. So we're going to go red to red. Now it's going into the multimeter. Now we've got a black coming out of the multimeter, and we're going to go back to V. Okay? We've got the black coming out of the multimeter, going back to V. So here is our circuit. V, we've got red coming out of V, going into M, the black coming out of M, going back to the power source. Now, we don't want these to touch, or we're going to short things out. Okay, so we want to keep these away from one another. Now, we're going to be measuring current, and so what we want to do is switch this multimeter over to current, and we've got it on ohms right now, but now we want to move it over to amps. Okay. And what one thing did I forget? What is this? The resistor. I forgot the resistor. We've got red coming out, going to M, red M coming out, and now we've got to go to the resistor. So let's look. Oops, we're going into M. We're coming out of M. We need the resistor in there. And the first resistor was brown, green, brown. So this is our first resistor. Are we predicting that this one, which has a very low resistance of 150.6 ohms, is that going to have a high current, or is that going to have a low current? Well, let's find out. We'll turn on the voltmeter. We got to make sure we went to current. I need to go down to the 300 ohms measurement. And we have a current reading of 28.99. 28.99, and this is in milliamps, actually. All right? Now, we can easily now put in the next one, which is brown, black, red. I should have put these in better order. Brown, black, red. Do we predict this is going to be lower or higher? Let's see. This was 1,000 ohms of resistance, and the multimeter says 4.49 amps, milliamps. Okay, much lower. Now, the next one is 18 in resistance, and that is the brown, gray, red. Brown, gray, red. That one is at 2.48 milliamps. And last one, the red, 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 which is 2200. And that should be lower. That one is at 2.06 milliamps. Was that what you predicted? Did that behave the way you predicted? Think about the higher the resistance, the lower the current, because remember, V equals I times R, Ohm's law. The larger R is, the smaller I has to be, because we did not change V. This whole experiment, we're going to be dealing with a voltage of 4.5 volts. All right, let's turn that off for a minute. And the next thing you're going to do is you are going to graph You're going to graph current as a function of resistance. As the current goes up, the resistance does what? So you can put numbers, you can draw a trend, whatever this graph or this data says. Remember, here's the current, here's the resistance, okay? If you want to use actual numbers, the resistance is going to go from 0 to 2200. Current is going to go from 0 to 29 if you want to use numbers, or you can just draw a trend. What is the relationship between current and resistance? Would it be the higher I is, the lower R is? Or would it be they both go up at the same time? As you increase current, you increase resistance. What kind of trend graph are you going to see? So you can either graph the actual data or you can just draw a trend, whatever you would like to do. Okay, now we're going to go to, and you answer this question here. We're going to look at our series and parallel circuits. A series circuit, there's only one path that the water can go. Pretend these are pipes. There's only one path they can go. A parallel circuit, hey, when it gets to this point, it can either go here or here. There's many paths. Another way to draw this very thing is you've got V here, and now you've got 3 different pipes. You've got 3 different paths that the water can go, and then it comes back to V. Okay? So this is the same thing as this. You've got many paths for that electricity or that water to flow through. Okay? It gets to a juncture and it could go here or it could go there or it could go there. Okay? So this is the same as this. The B stands for bulbs. So we're going to be working with bulbs. Okay? You can see in the series one path, in the parallel many paths. Okay? If you think of a pipe, huge gush of water comes to this point, it can either go through here, or through here. Okay. And then it comes back to the pump and goes through again. Okay. All right, so now you're going to make some predictions based on Ohm's law, based on V equals I times R. You will make some predictions. Go ahead, stop the video and make those predictions. I want to see good reasoning here if you're going for an A on the lab, okay? I want to see your predictions with reasoning using Ohm's law, V equals I times R. And now we are going to do some measuring, okay? And the data table for our measuring is, in series, the data table is on page 8. So basically what we're going to do is we're going to fill in this data table on page 8. And all of these questions go along with the data that is on page 8. So let's just look at this. Here's our series circuit. We're going to be using these 3 bulbs. And if you look, there is only one path that the electrons can travel on. Okay? Now, will these bulbs light as this is? No, they're missing a power source. You need a push of electrons in order to light the bulbs. Now, another thing is that instead of a resistor now, we are using B for the resistor. So this B here is the equivalent in this diagram of the resistor. Okay? So what you use, what you're powering the bulb, you can think of that as that resistor. Okay, so it says from the supply table, obtain a light board with bulbs, connect a single bulb to the power supply, record how brightly the bulb burns in that table. Okay, so we're going to just unhook the multimeter. Okay, so we're kind of done with that. And now we are going to be working with the circuit boards. And first we're going to be doing series. You're going to be making some observations, and again, we're going to put these observations into the data table on page 8. So let's hook up just one light and see how bright it shines. Okay? One light, brightness of bulbs. So number of bulbs, 1, 2, and 3. We are going to measure the brightness. So you're going to write down. So there's 1. And now I'm going to do 2. No, I'm not. Okay. I've got to move this one over here. There's 2. Do you notice any difference in the brightness between 1 and 2? Think of each bulb as resistance. Okay? V is the same. V is at 4.5. What's happening to the brightness? Now we're going to do 3. With 3 bulbs. So in this first part of the data table for the brightness of bulbs, you're going to put, very bright, less bright, not bright, whatever, however you want to describe. Let me show you again. This is 3. Okay. Here's 2. And here is 1. Okay. So record the brightness. And now we're going to measure the resistance. Okay, we're going to measure the resistance. Now, just like, remember when we measured the resistance? I've got to switch this over to resistance. Remember how we measured these resistors just by hooking them up like this? Okay. This was the 1800 one, this 1813. We're going to do the same thing with the light bulbs. All right? We're going to measure the resistance. And the funny thing is you don't need to have them on to do that. Just like these aren't on, right? We didn't have a power supply hooked up. So this has a resistance. I think at this point I need to go into the 10 amp. Okay. This has a resistance of 1.0 ohms. 2 has a resistance of 2.6 ohms. So you're going to write 1.5 ohms, 2.6 ohms. Look at 3. Remember, each of these, think of them like a resistor. 4.8 ohms. So we just measured the resistance. Put those numbers into the data table. And keep in mind the brightness. Remember, 1 bulb was super bright, and that had a resistance of 1, and 3 bulbs was very dim. That had a resistance of 4.6. Okay. Now we're going to measure the current through them. Thinking what we already know, if we could try to predict, and now to get the current, we are going to get the power supply back in here. We always go red to red, remember. Actually, what's cool about our new power supplies is they also will measure the current, so I don't need to use this. So that's kind of beautiful. Okay, so we're going to put the red at one end. This is where the power's coming in. We have to make it a circuit. So let's look at, this is the current going through 3 bulbs is 0.26 amps. Okay. Now let's go through 2 bulbs. Look at how much brighter it was than 3. So 2 bulbs, 0.31 amps. And now we're going to go 1 bulb, 0.45 amps. We have this entire data table filled out now. Now you can answer all of the questions previous to this data table. So from pages 5, 6, 7, and 8, you can answer the questions based on the data we just got. Okay? Now, one more thing about series circuits. See how dull they are again? What happens, so the next question says, another characteristic of series we'll explore involves what happens if we remove a device from the circuit. With the 3 bulbs connected and the power supply on, remove one of the bulbs. What happens and why? Remember, in series, there's only one path for the electrons. If we remove one bulb, look what's happened to them. Everything goes out. Thinking about your house. If you turn one thing on or you turn one thing off, if you turn something off, does your whole house go out? Could your house possibly be in series? Because in series, either everything has to be on or everything has to be off, because there's only one path for the electrons. There's only one path for them to go, only one way they can go, and if you remove that connection, everything goes out. Okay, so now let's move to parallel. Remember, you've already made predictions about parallel. And parallel, all these questions are going to apply to the data that we are getting. Okay? So this is our data on parallel. Let's look at the parallel compared to the series. Series, again, one path. But the parallel, you can see that there are many paths. Here, the electricity can go through this bulb or it can go down to this bulb. Okay? So there's more than one path in a parallel circuit. So now we're going to contrast them. So look at how bright 3 bulbs are in series. Let's look at 3 bulbs in parallel. 3 bulbs in parallel. The data table. Talk about the brightness of the bulbs. Remember when I unscrewed one in series and they all went out? Now look what happens. I unscrewed this. I removed it. Now I have 2 bulbs. Write down the brightness with 2 bulbs. And now I have 1 bulb. So write down the brightness in that first column, 1, 2, and 3. Remember in the series when there was 1 bulb, it was very bright, 2, much dimmer, 3, you could barely see it. Look at in the parallel. As I take out a bulb, what about your house? If you turn something off or on in your house, does everything else dim? Could it be in series? No. If you turn lots of things on in your house, does everything go down and, no. So thinking about your house, it's got to be in parallel, because even when you put more things on, it doesn't mean the other things are getting less power. Okay? Now, what's interesting is we still only have 4 volts, but now it's powering 3 bulbs very brightly. The brightness is related to the current. So how could they be getting a decent amount of current if there's so many things? Something must happen with the resistance in parallel that does not happen to the resistance in series. So let's measure resistance again. Remember, to measure resistance, we don't need that power supply. Remember how we just hooked this up to here without the power supply and got a resistance measurement? And then we did the same thing with those bulbs when they were off. So now we're going to do the same thing with resistance. We're going to go to that horseshoe, ohms, resistance. We make sure this is switched over to resistance. And let's start with one bulb. We're going to unscrew these. And with one bulb, I'll just take these out to make sure we've only got one. 1.1 ohms. Now, if voltage is the same, and with more bulbs, the current through the bulbs was the same, what must happen to the resistance in parallel? 2 bulbs, 0.8 ohms. Oh, went to 0.7 ohms. 1 bulb, 1 ohm, 2 bulbs, 0.7. What's going to happen when I add the third bulb? It's going to go up or down? 3 bulbs, 0.5 ohms. The resistance goes down. The voltage stays the same. We have 3 bulbs. We have to have an amazing amount of current because the bulbs are really bright. Okay? So we just did total resistance, and now we're going to measure the current. We're going to measure the current. So we are going to, again, get this thing out of here. And boy, this lab, when there's 5 tables going and all this equipment and this is a really nice, basically students be ripping their hair out at this point in the lab trying to get all this data because, our equipment's not 100%, perfect, and it's just, this is a really nice way to do this lab actually. Okay, so we want to measure the current in the circuit for 1 bulbs, 2 bulbs, and 3 bulbs. If the resistance was going down, what do you think is going to be happening with the current? 1 bulb, 0.4 amps. 2 bulbs, 0.85 amps. And where it says current through each bulb, all you're going to do is take that 0.85 divided by 2 bulbs. That's the current through each bulb. So 1 bulb is 0.4, 2 bulbs, 0.85 divided by 2, and 3 bulbs is 1.30 amps. And for that one, current through each bulb, 1.30 divided by 3. These bulbs are nearly identical. The beauty of a parallel circuit is that the resistance goes down the more things you put into the circuit. Now, this is a problem in your house because the more things you turn on, what happens to the resistance? The resistance goes down, but the current goes up, and wires can only handle so much current before they start to burn. So you have, if you have a very old house, you have fuses, and if the current gets to a dangerous level, the fuse will blow. And that's a symbol, that's a signal to you, I have too many things on in that particular circuit, I need to turn something off. Up north we have a cabin, and that cabin is supplied, it's got 22 amp wire, and so if someone's blow drying their hair and someone else is using some, a DVD or something, it will blow. And some people think they outsmart the fuse and put a penny in there to stop it from working, what they're really doing is dangerous, because when current has more wire than it's rated for, or when wire has more current than it's rated for, it will burn and you get an electrical fire. So never mess with, if you have a circuit breaker, if you have a newer home, instead of having a fuse, you have a circuit breaker. And so when you have too many things on and a dangerous amount of current is coming, because as you turn more and more things on in parallel, the resistance goes down, that means current goes up. If there's too much current, your wires will, your circuit breaker will break. Your circuit will break, everything in that circuit will turn off, and you got to go down and flip the circuit breaker back. And there's usually like a red line or something. But you got to turn something off because you have too much stuff on for the amount of current the wires can handle. In the factories, the wires are, can handle a huge amount of amps, a huge amount of current. My cabin up north, 22 amp. I think most newer construction, they're dealing with like 200 amp. Older homes have like a 60 amp. So amperage is current. Too much current is dangerous when the wire can't handle it. Okay, so now let's look again. What happens when we unscrew a bulb in parallel? Nothing. The other two things are fine. In fact, when we unscrew it, what happens to the current? Strangely enough, the current goes up. Because remember, the more things you have, it's like that water and the pathways. If you have a pipe of water and it has 100 paths to go through, then a little bit is trickling through each path. You shut one of those down, more goes into the other 99. So if you think of electricity like water, a lot of things make sense. Okay, so you have the questions that applied to parallel, which was pages 8, 9, and 10. And now you just have some basic questions to finish up. What happens if you add a fourth resistor in series, a fourth resistor in parallel? You got to think of what we just discovered with that data. And then it talks about why do we have fuses. You got to summarize your knowledge. If you're going for the A in the lab, you need to really spend a lot of time on these questions. Great job. That's it for our Inquiry into Simple Electric Circuits lab.